I'm very happy to introduce Said Zakeri, who's going to talk about near-parabolic points and Hausdorff limits of external rays.
So, are we waiting or? Okay. It's a great pleasure to speak at this conference where we celebrate Carsten's 60th birthday. I've been very fortunate to work with him as a colleague for more than 20 years and also get to know him as a friend for same length of time. And he's been a great source of mathematical inspiration, for sure. But also, he's been an example of kindness, generosity in his ideas, and modesty. So I just want to say happy birthday again. And I wish you a great birthday this year and many more to come. So what I want to talk about today is joint work with Carsten on Hausdorff limits of external rays. It's a basic question in polynomial dynamics, which we felt is worth studying, and probably people didn't look at it in great detail. So let me first set up some standard notation. CD is the connectance locus of polynomials of degree D. For a polynomial P, J sub P and K sub P, as usual, denote the Julia set and the field Julia set. Omega sub P is the basin of infinity, the complement of the field Julia set. And beta sub P is the Butcher coordinate, mapping basin of infinity to the exterior of the closed unit disk conformally and conjugating the action of the polynomial to the power map Z goes to Z to the D. And the main players are the so-called external rays. So you fix some angle theta, mod 1, and the external ray at angle theta for the polynomial P is denoted by this symbol, R sub P of theta, which is you just take the straight radial line at angle theta outside the closed unit disk, and you pull it back under the Butcher coordinate. You get an embedded arc. So this is as far as the notations go. Now, let me pose the main question. Let's assume we have a sequence of polynomials, say Pn, in the degree D connectedness locus, and this sequence converges to some polynomial P. Throughout the discussion, I'm going to fix a periodic angle theta under multiplication by D. So this is a periodic ray, and we know that such a ray lands at a periodic point, which is either repelling or parabolic. The external ray at angle theta for the polynomial Pn, I'm going to simplify the notation to R sub n. So R sub n is the theta ray for the polynomial Pn, and R is the theta ray for the limiting polynomial P. And when I take the closure of a ray, namely, I take the union of the ray with the landing point, I use this notation, Rn bar and R bar. So the question is, what are the possible Hausdorff limits of the sequence of closed rays? It's been known for a long time, and this is an easy exercise, that if the landing point of the theta ray for the limiting polynomial is repelling, then the whole picture is stable, and this sequence of closed rays will converge in the Hausdorff metric to what we think it should converge, which is the closure of R. So nothing interesting happens if the landing point of R is repelling. However, if the landing point is parabolic, then it's been observed for, again, a long time that you can get some extra stuff in the limit. So you could come up with examples where when you take the Hausdorff limit of these closed rays, not only do you get the closure of R, but you get some extra stuff. So let's take a look at some examples. This is already in a the angle is rational, so we know it's periodic, so we know that, yeah, of course, if theta is irrational, then all bets are off. This example already appears in an old paper of Goldberg and Milner. It's a cubic polynomial with a non-degenerate parabolic fixed point here. Both critical points are in this basin. The ray at angle 0 lands there. It's a real polynomial. You can take suitable perturbations so that this parabolic point splits into two nearby attracting points, and the field Julia set has this channel. This channel opens up, and the 0 ray for this perturbed map passes through this channel and lands at a faraway repelling point. So when you choose the sequence of perturbations carefully, you can end up with Hausdorff limits in the limit, which not only contains this limiting ray, but some extra curve connecting the parabolic point to a faraway repelling point. So something like this picture already appears in the paper by Milner and Goldberg. Another work that has the same flavor is an old thesis of Richard Otkirk, student of Tanley. He doesn't consider external rays per se, but he studies various perturbations of parabolic points and the way the so-called gates will open up and various patterns. So it's related, although it's not exactly the same problem. So this is the example of a cubic with a degenerate parabolic at the origin. It's z cubed plus z. And you can find perturbations. You can find perturbations such as this one. So now, this being a degenerate parabolic, it splits into 3 nearby fixed points. So you can choose the perturbations so that 2 of them are attracting, the third one is repelling. Again, you see a gate opening up here. Oops. So much. Okay. So a gate opens up here, the 0 ray. So the 0 ray lands at this parabolic fixed point. And if you look at the 0 ray for the perturbed polynomial, it passes through this channel. It makes a turn, and it comes back and lands at that repelling point. So provided you choose the sequence of perturbations carefully, what you get in the limit is the extra stuff that you get will be a loop connecting that parabolic point to itself. I'm sorry, is this too loud? Is it? Okay. Okay. And of course, the third example is comes from the classical theory of parabolic implosion. You could even go to the quadratic family. This is, as far as I know, it started with Duarry's ideas, and then Lavor's, and I'm sure a lot of other people in the subsequent years. So this is just the good old z squared plus 1/4. The zero ray lands at that parabolic point, and we can choose careful perturbations so that the parabolic point splits into a pair of repelling points. And the zero ray for the perturbed polynomial comes in, and it falls into this infinite spiral. And provided that you choose your perturbation carefully, you can arrange that as n goes to infinity, as you approach the parabolic, those turns in your spiral won't die. And what you get in the limit, the extra stuff, will look like a Hawaiian ring. It's going to be a countable sequence of ovals, nested ovals, going from the parabolic point to itself. So this question, studying possible limits of Hausdorff limits of external rays, to me it seems very natural, worth studying, but we had an added motivation. Carsten and I have been working on a joint project in the cubic family, which gives us a description of some limbs in the cubic connectedness locus in C2, two-dimensional complex. It's some kind of generalization of intertwining surgery when we describe cubic polynomials that have two quadratic pieces, but the combinatorics is more or less arbitrary. So in that context, such limiting process becomes relevant, and that was one of our motivations, but I'm not going to talk about this. So let me set up the question more accurately so we can have something explicit to work with. So here's the situation. I have a sequence of, I don't know what's wrong with this. I just changed the battery and it's supposed to be new. But, okay. I have to turn it every once in a while. Maybe I should go to the other one. Okay, this works for now. So Pn is a sequence in the degree d connectedness locus that converges to a limit p. Theta is a fixed periodic angle under multiplication by d. Throughout, I'm fixing theta, and it's a periodic with period q. I have the rays Rn for the nth polynomial and R for the limiting polynomial, and I'm denoting the landing points by zeta n and zeta. So zeta n is the landing point of Rn, zeta is the landing point of R, and after passing to a subsequence, I can assume that zeta n converges to some limit zeta infinity, which, and that's, as a matter of fact, one of the main points, zeta infinity could be different from zeta. In other words, the limit of the landing points could be different from the landing point of the limit. And I can assume that the closure of Rn, which is Rn union its landing point, has some Hausdorff limit, which I denote by L. So that L is some Hausdorff limit along some subsequence. And my goal is to understand the possible structures of these continua. What could we say about L? So there is a trivial observation. Whatever this L is, it must be invariant under the qth iterate. And the piece of L in the basin of infinity is just R. So if you get extra stuff, it has to be in the field Julia set. So this is trivial. Now I'm going to give you two lemmas. These are just first reductions of the problem. The first lemma is very easy, and the second lemma is not very difficult. So first lemma is L intersection with the Julia set is finite. So as a matter of fact, if you pick any point in L intersection with the Julia set, it has to be a fixed point under the qth iterate. So whenever I have a symbol without the subscript n, that refers to the limiting polynomial. If you see a subscript n, that's for the nth polynomial. So the proof of this is very simple. Let omega n be the basin of infinity for Pn. Take a sequence un. On the nth ray approaching u, by lower semi-continuity of the Julia set, since u is in the Julia set of the limiting polynomial, the Euclidean distance between un and jn, the nth Julia set, must go to 0. So un is approaching the boundary of the basin of infinity. Now, the hyperbolic distance in the nth basin between un and its qth iterate is uniformly bounded. Because you're on a ray, you're just applying the map q times. So there is a uniform bound for this hyperbolic distance. These 2 points have bounded hyperbolic distance, and they go to the boundary. One of them goes to the boundary. So the Euclidean distance should go to 0. So the Euclidean distance between un and its qth iterate goes to 0, which means that u is a fixed point under the qth iterate. So whatever points of L in the Julia set, there are finitely many of them, we're going to describe these fixed points shortly. So they can't be any arbitrary fixed points. The second lemma, so what remains to be understood is the intersection of this continuum L with the interior of the field Julia set. And this is what the second lemma addresses. So the second lemma is that L intersection with the interior of K is a disjoint union of embedded arcs. So more specifically, every point u in the intersection of L with the interior of the Julia set must be in a parabolic basin, which is fixed under the qth iterate. But moreover, so this is u, and there is a parabolic basin, B, which is fixed under the qth iterate. But this u is contained in some simply connected domain inside that basin. I'm going to call that V. You should think of this V as some kind of a band or infinite strip. So there is such a neighborhood V and some conformal isomorphism C from V to the right half plane, normalized so that it sends U to 1. And it conjugates the action of the qth iterate with multiplication by d to the q. So this basically shows that every point in L that is in the interior of the field Julia set has this sort of canonical neighborhood in which the action of the map is well understood. It's pretty much like a translation on this strip. And moreover, if I consider the real slice here, the set of positive real lines, this arc, and pull it back under C, I get an embedded real analytic arc passing through U. The claim is that, first of all, this arc is completely inside L, so it's inside your Hausdorff limit. And both limits, W minus is, so this arc is more or less canonically up to multiplication by Carsten, is canonically parametrized by this interval 0 to infinity. If you go back in time, it has a limit as t goes to 0. That's what I call w minus. And as t goes to infinity, in the future, it has a limit. That's what I call w plus. These two limits exist. Both are fixed points on the qth iterate of the map. And the plus, the future limit, must be parabolic with multiplier 1 under the qth iterate. But the past, w minus, could be parabolic or repelling. We don't know that.
So w minus can be equal to w plus?
Yes, yes. So we'll see that case on the next slide, maybe, or the slide after that. So what is the sketch of the proof here? It's an application of basic ideas in Carathéodory convergence, which goes back to the work of Carsten on, I think, when you were trying to give a different proof for landing theorems in, for the Mandelbrot set. So the main idea in this proof is that if you have a sequence of topological disks, like which are pointed. So you specify a base point, and imagine that in the Carathéodory limit. So we know that when we take the Carathéodory limit, pieces of this can pinch off, and they can disappear. So maybe you get something like this. I don't know. So this would be, so if I call this region U, this would be an example of Carathéodory convergence, which basically means convergence of Riemann maps. So given such a situation, if I change the base point from Pn to, say, Qn, such that the hyperbolic distance between the two is uniformly bounded, so if the hyperbolic distance in Un between Pn and Qn is bounded, then with the new base point, if you take the same domain, but with the new base point, that converges to the same domain U with a new base point, perhaps after passing to a subsequence. So maybe Q is here. So moving the base point a bounded distance will not change the Carathéodory limit of the domain, but it'll change the base point, of course, but you'll get the same limit. However, if I choose, I don't know, let me choose this color. If I choose, oh, that's not good. Say Rn. If I change my base point to a different point where the hyperbolic distance is growing, then the claim is that provided that the spherical distance between this point and the boundary is bounded below and above, so you can extract the Carathéodory limit, what happens is that the limit will be a completely disjoint disk. So that's the second part of this lemma, that if the distance Un, Pn, and Rn goes to infinity, then after passing to a subsequence, and plus another technical condition, which is not important now, Un, Rn, will converge to some Carathéodory limit V and R, where the disk V is disjoint from U. So if you move the base point farther and farther away, what you get in the limit is a completely disjoint. So that's the basic idea in proving that lemma. And the idea is you have your point U in L, but it's in the interior of the field Julia set. you take an approximating sequence un on the nth ray.
Sorry, this is after passing through a subsequence.
Yes, of course. Both of them. Yeah, it's a compactness argument, so yeah. So let's take a sequence un converging to u. This time, so un is on the nth ray. We can assume that this point u, which is an L intersection with the interior of the Julia set, is not fixed under the qth iterate, in which case it follows from lower semi-continuity of the Julia set that the distance between un and jn is bounded above and below. And that is the type of condition that I need for extracting Carathéodory limits of subsequences. So let Sn be the Green's potential of un. So Green's potential with respect to the nth polynomial. So Sn goes to 0, because if it doesn't, then the limit would be in the basin of infinity. So the nth point, approximating point un, has a Green's potential in its own dynamical plane, that's Sn, on the nth ray, and that sequence has to go to 0. Now, the punchline is that if you take the basin of infinity omega n with the base point infinity, you have this Carathéodory convergence. Omega n with the base point infinity goes to omega with the base point and infinity. This is just continuity of the Butcher map with respect to the parameter. However, if I change the base point from infinity to un, since un, so the distance, the hyperbolic distance between un and infinity is controlled by that potential, and the potential is going to 0, that hyperbolic distance, there is an obvious estimate. That hyperbolic distance goes to infinity. So we are pretty much in this case, where this is infinity and this is un. So they're getting farther and farther apart, and this is the basin of infinity. So when I go to a limit, it follows that with the changed base point, when I replace the base point infinity with the base point un, now this sequence, omega n un, goes to some Carathéodory limit, v and u, where v is disjoint from the basin of infinity. Therefore, v is a disk inside the field Julia set. So this is the construction of that neighborhood v. And then what you do is you construct your conjugating map C as the limit of a sequence of appropriately normalized. So you take, you basically rotate your Butcher coordinate, then you take suitable logarithmic branches, and then you normalize it by the potential. You use a normal family argument, you extract the limit. And the fact that this curve, gamma, that I showed in that slide, it has a future limit and a past limit. This is just simple hyperbolic geometry estimates. And the fact that W plus is parabolic with multiplier 1 is Snell lemma. So that's just automatic. So what follows from this second lemma is that L intersection with the interior of the field Julia set is a disjoint union of invariant arcs. They're real analytic. For simplicity, I'll call them L arcs. These are all inside parabolic basins. And they are parametrized by the dynamics. The dynamics is like a translation of them. Every L arc gamma is contained in an invariant band V. That's the simply connected domain that we constructed. We have that conjugacy. And the only part of L in this band is gamma. So that's a simple lemma. So every such arc, such what I call an L arc, is contained in a band which sort of shields it from getting close to other L arcs. And in particular, there are only countably many L arcs. So there are two possibilities, as Mitsu observed. The two endpoints of an L arc could be different. W minus and W plus could be different, in which case we call it a heteroclinic arc, and they could coincide, forming a loop, in which case we call it a homoclinic arc. And every maximal nested chain of homoclinics is called an earring, for good reason. Now, how many loops do I get in an earring? We don't know. It could be a single one. It could be infinitely many loops, like in the parabolic implosion case in the quadratic family. So, but we take this class of maximal chain of nested loops, and we call that whole thing an earring. It may be just one loop. So now we have the first theorem, which basically describes three possibilities for L.
Sorry.
Yes.
Go back to your earring then.
Yeah.
So your earrings don't necessarily all have to be the same.
In the same what?
You all have to be the same parabolic basis.
Yes, yes. I mean, from this definition, for example, it's not quite obvious that there is an outermost loop for an earring. I mean, for all we know, it could look like this. So, and then infinitely many going out. We rule this out, of course. So if there are infinitely many, there has to be an outermost. And then maybe you get something inside. Maybe you get infinitely many. But yeah, they all, so when I talk about an earring, the same parabolic point could have like two different earrings attached to it. So these are considered different. And this happens in different basins, like different petals. Yeah. It's related to, yeah. So the three cases that can happen to this Hausdorff limit L, the first case that we call the tame case is when L is just a closure of the ray R, in which case, so remember, zeta was the landing point of R, and zeta infinity is the limit of the landing points zeta n. Sorry, what happened? So in the tame case, nothing interesting happens. Zeta and zeta infinity are the same, and L has no extra decorations. That is, for example, when zeta is repelling. But in general, in the tame case, zeta could be repelling or parabolic. Both of them can happen. The second case is what I call semi-wild. So L does have extra decorations, but still zeta and zeta infinity are the same. So limit of the landing points is landing point of the limit ray. But in this case, the only thing that can happen is that, so L is strictly larger than the closure of R, but the only thing that can happen is some extra homoclinic arcs connecting that point to itself. One or many, at least one. And the third case, which is wild, is when zeta and zeta infinity are completely different. And the claim is that now that these are different points, there has to be a unique chain of heteroclinics connecting them. So there is a unique chain of heteroclinics, gamma 1, gamma 2, etc., connecting zeta, which is the first landing point of R, to zeta infinity, which is the end of this chain. the end of this chain. So there are finitely many parabolic points on the way. I'm not describing the full set L. I'm just saying that L contains this unique chain of heteroclinics. Now, what you said is on the next slide. So, yes?
Is the chain not necessarily real analytic, only piecewise?
It's piecewise analytic. No, you could definitely have angles, as I indicated at WK. Yeah.
You might be going to one of the calculators.
What's that?
You might be going like any one of the different.
Exactly. You may go to a parabolic point in some direction and then go off in a different direction. Yeah. Now, let's call this the union of the ray R in blue here, the union of that ray R with the chain of heteroclinics and their endpoints. Let's call that the spine of L. And this is something uniquely defined. It's canonical. You can't find two different chains like that. So that's what I call the spine S. Now, if there are no heteroclinics, like in the tame case or in the semi-wild case, then the spine is just one point. So it degenerates to a point. And theorem B is either L is just the spine, or else the extra stuff in L that are not in spine, they can only be finitely many earrings of homoclinics based on those parabolic points Wj. Moreover, every parabolic basin contains at most one earring. You can have more than one. And if you take a look at, say, W1, W2, all the way to WK, if there are any earrings attached to those points, they have to be single loop. The only place you can have a Hawaiian earring is the last one. So you could have a loop, say, at W1, but if that happens, it has to be a single loop. You could have, so at WK, that's an example of two different earrings, so they should happen in different parabolic basins, but they're single loop earrings. But maybe if there is a Hawaiian earring, it has to happen at the very end. So the proofs of theorem A and B are achieved in various stages. The first thing you do is there's a finiteness argument, because in the beginning, you don't know how many L arcs you have. So what you prove is that every parabolic basin contains at most finitely many heteroclinic arcs, and at most two earrings of homoclinic arcs. So this is a modulus argument. So if you take a parabolic basin and look at the, say, heteroclinic arcs with their bands, when you go to the quotient cylinder, so this is C over Z, you get an annulus, and that L arc maps to the core geodesic of that annulus. And the modulus of this is independent of all choices. I think it's pi over Q log D. So in the quotient, when you take the band around every, say, heteroclinic arc in the same basin, in the quotient cylinder, it looks like an annulus with this definite modulus. So what you prove is that any such thing should separate at least two critical points. So each half of it should contain a critical point. There are finitely many such critical points. If you have infinitely many of them, then what happens is you have infinitely many such annuli, and they all separate at least two critical points, and they're disjoint and essentially embedded. Since all of them have the same modulus, it follows that between these two critical points, you can fit annuli as fat as you want, but that's a contradiction because there is a bound on the modulus of the annulus that you can fit separating in that cylinder, separating 2 points. So that proves that there are only finitely many heteroclinics in every parabolic basin. You prove something similar for homoclinics. Basically, if you have a homoclinic, it should cover one end of the cylinder. Cylinder has 2 ends, so you get at most 2. But of course, we refine this. So this is the first step. You go from arbitrary countable number of L arcs to finitely many. And then you refine it further. So up to this point, it follows that the spine is a finite tree. And you prove using this first step that L is path connected. So the spine is a finite tree, but for all we know, it could look something like this. And then we have to rule this out. We want to show that the spine is actually homeomorphic to an interval. It doesn't have those branch points. And what you do here is, so uniqueness, so basically, then from finiteness, you want to go to uniqueness. You want to show that every parabolic basin contains at most one heteroclinic and at most one earring. So from finitely many and 2, you want to go to 1. You want to reduce that. And one concept that becomes useful here is what we call the intrinsic potential order on these L arcs. So every point on an L arc is the limit of a sequence of points on the corresponding rays, whose Green's potential go to 0. So you're dealing with sequences of potentials going to 0. All of them go to 0. But it turns out that there is a hierarchy between them, how fast they go to 0. So the way you define this natural order is that if you have 2 points U and U prime in L intersection the interior K, if, say, Rn of Sn, so the point at potential Sn on Rn goes to U, and Rn S prime n goes to U prime, then these potentials are not well defined, but they're well defined up to a factor which goes to 1. So that defines equivalence classes of sequences of potentials going to 0. And you define this order. You say U is less than U prime when, oh, I think I have it here. So instead of writing it, I can show it here. So you define U to be less than U prime when S over S prime, both of them are going to 0, but if the limit of the ratio is less than 1. If this limit is, it's a positive, it belongs to 0 and infinity included. If it's a positive real number, strictly between 0 and infinity, you get 2 points on the same L arc. But if you have, for example, if you're here, so we know that this is a directed graph. It's directed by the dynamics. So there is an orientation on each piece. But there is also a hierarchy between 2 different, which comes from that order. So for example, if you pick your U here and your U prime here, then U is less than U prime, and that ratio of the potentials is 0. So this notion of who comes first along this spine will allow you, because this gives you a sense of this spine is some kind of a trace of how the ray at the nth level behaved, which we don't see it now. But it gives us a sort of rough measure of the complexity of the actual ray. And using this order and some topological arguments, we can prove that. So this requires several lemmas, but you break it down into various statements. You go from a finite tree to just an interval. So let me talk about a few other related results. Sure.
Do you have a method to build examples of, say, a large degree where you can?
Not the full method. So that's one of the problems, whether or not we can. So given a pattern, can you generate this L? I suspect the answer is yes, but we don't yet have the full realization theorem. This is very new, so we're working on it. It's a preliminary report. But I do have some example that's coming up. Yes?
Just to make sure, do you have an easy estimate of the length of the spine in terms of the degree?
Yes, it's on this slide. Yeah, I'm masking half of it, but it's coming up. Yeah. So let n sub het be the number of heteroclinic arcs, and n sub hom be the number of cycles of earrings, of homoclinic arcs. Then the corollary of this construction is this estimate. Twice the number of heteroclinics plus the number of cycles of earrings is less than or equal to d minus 1, simply because, so every earring of homoclinics is in its own parabolic basin, cycle of parabolic basin, so it requires one critical point. But the important, so why is this 2 here? Because every time you have a heteroclinic, in a basin, you need at least 2 critical points. So this observation, this proof is based on the observation that if you have a parabolic basin B containing a heteroclinic arc, and that's unique, if you have a heteroclinic arc in a basin, that's it. You can't have anything else in that basin. Not another heteroclinic, not any earring of homoclinics. Then the qth iterate of the map, sending that basin to itself, is proper of degree at least 3. So it has at least 2 critical points in that basin. So this puts a restriction on the, yes?
How are you counting the number of cycles of earrings?
Okay. So this puts a restriction on the topological complexity of L that you can get. For example, if so this shows that if these two, I'm just talking about non-tame wild or semi-wild cases, this is the only thing you can have, like in the parabolic implosion example. If D is 3, so in particular, you can't have a heteroclinic. If D is 3, in addition to this, so you can have this. You can have this with a single loop, and you can have something with a single heteroclinic.
Can you not have that one loop and then earring attached to the other side with one type of another?
Where? Here or here?
Yeah, in the middle one, not go on with others.
No, not in the cubic case, in higher degree case, because this, a single loop homoclinic, you should think of it as a heteroclinic. This kind of single loop homoclinic is very different from the Hawaiian earring. So if you have this in the cubic case, you can't have anything else. That already, when you perturb this, that already creates 3 nearby fixed points. But in higher,
When d equals 3, d minus 1 is 2.
yes, yes.
So can you have a 2, 1 heteroclinic plus 1 homoclinic?
So one heteroclinic already eats up everything. So you hit the top. And in the cubic case, if you have one heteroclinic, already you have two on the left side, so you can't have anything else.
So you were drawing the picture with 1 and 1?
No. So in this case, it's just the ray. And so this is just the ray. Yeah, maybe, yeah, the picture is not clear. So this is just the ray and a single loop homoclinic, and this is just the ray plus one single heteroclinic. Right, right. There are things that definitely that's a very crude estimate. You can do much better, and that's another thing that we're working on. This is the crudest estimate. But for example, the idea that this single, it doesn't follow from that. The idea that this thing should be treated as a heteroclinic is not encoded in that inequality.
Can you have two theory?
I'm sorry?
Can you have two theory?
Sure, yeah, but in higher degrees, yeah. It would be, I think, yeah, degree 5, definitely you can have it.
But it can't be for 4.
Probably not. You mean two earrings attached to the same parabolic? Yeah, yeah, yeah.
But you had the ordering coming from the potentials. What are the ordering between two earrings?
It depends on the sequence of perturbations. So I think you know that the ratio of the, so one of them is less than the other one. So you know that the ratio goes to 0 with some speed, but I think depending on the, it depends on the multiplier, how it goes to 1. Yeah?
So there's a point here you write the number of cycles.
Which,
You have a rotation number at the end,
right,
so that you can have a cycle.
right, right. Of course, that's another thing that we would hope to improve if, degree 2, the quadratic case. Right, right. For the last point, yeah, yeah, for the last point. Yeah, yeah, yeah. Yeah, that's why we say cycles of earrings, yeah. But I think their question was 2 different cycles. Yeah. I'm sorry, how much time do I have? 4 or 5 minutes? Okay. 10 minutes? Thank you. So this is related to your question, Laura. So this is a maximally wide polynomial example. We can construct examples of polynomials of odd degrees which have the maximum number of heteroclinics. And one reasonable way of constructing them is described in this theorem. So for each k, k is the number of heteroclinic arcs that I can create. There are real numbers, W1 bigger than W2, bigger than, etc., WK. These are all positive, and WK plus 1 is 0. So like in this picture, you can find k positive numbers, W1 through WK, and a real monic polynomial P of degree 2k plus 1, which has a repelling fixed point at the end at 0, but all the other WIs are parabolic of multiplier 1, fixed point, parabolic fixed points of multiplier 1, with the condition that the residue iterative at each of these parabolic points is negative. And that is the condition that guarantees that when I perturb this polynomial, I get a pair of attracting fixed points. So there is such a polynomial. For each k, we can construct this. It's completely symmetric. It's a real polynomial. And if I perturb these polynomials by adding a small positive number, say p sub n is p plus 1 over n, then what happens is that each of these parabolic fixed points split into a pair of complex conjugate attracting fixed points. So that gap opens up. There are no critical points on the way. The 0 ray for the perturbed polynomial has nowhere to land but the last one, because you've already exhausted all possibilities. Nothing else. There is no other room for it to land. So for all nearby polynomials, the zero ray lands here, but for the original polynomial, the zero ray lands here. So everything in between must be heteroclinic. So that way you construct such a polynomial. Of course, the non-trivial part is to guarantee that there is such a polynomial with the condition on residue iterative. But that's pretty much calculus. So this is an example when k is 2, degree 5. So you see a parabolic point here, a parabolic point here, and a repelling fixed point at the origin. When you take the small perturbation, a channel opens up here, a channel opens up here, and you have now 4 basins. These 2 basins are doubly pinched. They're pinched here, and they're pinched here. And there is this basin, for example, goes all the way through this channel and has this repelling fixed point on its boundary. And if you have more for higher degrees, all of them should have the repelling fixed point at the origin on their boundary. So, and back to your comment, Sabia, this is pretty much, you see the formation of that character limit V. So it's right here, that the band. So let me just mention that this is maybe the first part of an ongoing project. Carsten has convinced me that there is a very useful gadget in parabolic perturbation theory, which is one form used by Xavier Bouffe. And he's a strong believer in what you can do with this, and I'm convinced. So let me just tell you that in this example, in this theorem, when you take the perturbation, so these points have a pair of complex conjugate multipliers that as n goes to infinity, they go to 1. Those multipliers go to 1. But they go to 1 horocyclically. They can't go to 1 tangentially, for example. It follows from the construction. And the question was, how can we guarantee, I mean, once you perturb a parabolic point, what is it that guarantees that the gate opens up and you pass through it? It's a near miss, or maybe you're just trapped there and land. So that was the question. And using this gadget that I was referring to, we have a result. And it turns out that non-tangential versus horocyclic convergence of the multiplier is the key. And so let me quickly, and this is my last part of the talk. So let lambda be a primitive qth root of unity. Take a polynomial with a fixed point, parabolic fixed point at the origin of multiplier lambda, the qth iterate. So I'm assuming that it's non-degenerate. So I can put the qth iterate in this normal form. So zq plus 1 is the first non-zero term, and then some constant a times z to the power 2q plus 1 plus higher terms, and this parameter a is just the holomorphic index. So I'm assuming that we're in the non-degenerate parabolic case. And consider a sequence of perturbations of this polynomial. So you perturb lambda to lambda n, such that the qth power of lambda n now goes to 1, but let's assume that it's never equal to 1 in absolute value. So under this assumption, for nearby polynomials Pn, the parabolic fixed point at the origin bifurcates into a single fixed point at the origin of multiplier lambda n, and a q cycle around it, which I call O sub n, of some multiplier mu n. There is a relation between mu n and lambda n. But so you have this fixed point at the origin, and you have a cycle around it, which asymptotically looks like it's a q cycle. Asymptotically, it looks regular. So asymptotically, they look like vertices of a regular hugon. Now, it turns out that if I if I let lambda n to the power q goes to 1, which is equivalent to letting mu n goes to 1 non-tangentially, then they must have different sizes. One of them should be less than 1 in absolute value, the other one should be more than 1, which means in that case, either the origin is repelling and the q cycle is attracting, or vice versa. So we are in that situation. And the theorem is, so you take such a polynomial p, unperturbed polynomial with a parabolic fixed point at the origin, and you assume that there is a ray at some angle theta landing on it. If, so remember lambda n to the power q, these are the multipliers of the perturbed map. If lambda n to the power q goes to 1 non-tangentially, then for all large n, the ray, the nth ray, the theta ray for the nth polynomial lands at the origin if lambda n is, if the origin is repelling, so lambda n is bigger than 1 in absolute value, and it lands on one of the points in the q cycle if mu n is bigger than 1, if the origin is attracting and mu n is, and on is repelling. And you have tameness. So Hausdorff limit is the smallest possible you can get. So briefly, this theorem says that non-tangential approach of the multiplier implies tameness. So this is an example of a cubic polynomial with a parabolic fixed point here, 3 rays landing on it. If you take the perturbation, non-tangential perturbation, where the origin is repelling and you have an attracting 3 cycle, you still have the landing. And you can't twist it enough to create weirdness. And this is the case where the origin is attracting and you have the nearby 3 cycle repelling, so you have exactly the same behavior of landing tamely. So the case where the multiplier goes to 1, the qth power of the multiplier goes to 1 radially, had been proved by Milner in his paper on the combinatorial study of the Mandelbrot set. So this is a generalization of that statement. He did it by choosing a clever normal form, but going from radial convergence to, usually in complex analysis, going from radial to non-tangential is very easy, but not in this case, because once you go out of radial, then things could twist. So I just want to mention this, at least mention this gadget that Carsten has been advocating for. This is what we call Booth 1 form. So you take the qth iterate of your map, which is a near-parabolic map. And the classical form that one uses in parabolic perturbation theory is dz over z minus the map, using which you define the index and whatever. But it was Booth's observation that if you're willing to make this a little more complicated looking by incorporating this extra term, 1 minus the derivative on the top and logarithm of the derivative on the bottom, there is a well-defined branch of this logarithm, then this form is, has extra properties that are very useful. For example, if you have, so if you take one of these forms, the residue of this form at a fixed point is just, so this form is a meromorphic form which has poles at the fixed points of the near-parabolic map. So this residue is 1 over log of the multiplier if the point is not parabolic, and it's the residue iterative of the map at the fixed point if it is parabolic. So these properties are very useful. And the idea is, so this is the main player in our proof. The idea which goes back to work of Carsten on double parabolics, more than 10 years ago now, 20 years. The idea is that the straightening map of the Booth form, if you integrate the Booth form, you get a nice pre-Fatou coordinate for the near-parabolic map. So this is a multi-valued function, so you have to work on a Riemann surface. There are singularities, so when you go around them, you have monodromy. But in a sense, when you compute this multi-valued function on an iterate and subtract the multi-valued function, you get rid of the ambiguity. So you get a very nice measure of, well, it's a pre-Fatou coordinate. So this difference is well-defined, holomorphic, single-valued, and it's very close to 1 in a neighborhood. So the idea is that you use a suitably rotated version of this Booth form to construct trapping regions around the fixed points where the ray is supposed to land. So once you have these invariant regions that don't shrink, you can show that once the ray comes in, it has nowhere to go. There is no gate open for it, so it's trapped, and it has to land. I'm sorry I went over time. Thank you.